So let's start the second session of the morning session of the HoTT-UF on Sunday. And the first speaker of this session will be Matthias Hutzler from the University of Gothenburg, who will tell us something about the foundation for synthetic algebraic geometry.
Thank you. Thank you very much for having me here. And yeah, I'm excited to give this talk about this project. And yeah, it's joint work with Felix Carabini, who is present here, and with Thierry Coupon, and I will mention some other people later. And yeah, let me just dive in. Synthetic algebraic geometry. I should make some acknowledgements first. So this approach on synthetic algebraic geometry, we didn't start it from scratch. It's based on work by Ingo Beckschmidt, Anders Koch, and David Chesmeyers. And also to mention that the approach to cohomology used is the one that was proposed by Mike Schumann and worked out later by Floris van Doorn. And yeah, here are some more people who are actually now actively involved in developing this theory. Ingo Beckschmidt, Hugo Moyneclé, who is present here, Jocelyn Corré, and David Verne. David Verne is also here, over there. And yeah, here's roughly who's working on which such projects right now, but it might even be a little bit outdated already. Okay, and you can find unfinished drafts on Felix's synthetic Zariski. All right, but now, what is synthetic algebraic geometry? Well, what it means is that we take HoTT as a language and add some axioms to it. 3 axioms to be precise. And these axioms let us work in a way which is yeah, very intuitive from an algebraic geometry perspective. So algebraic geometry is about thinking about algebraic problems in a geometric way. This is at least the basic idea. So the basic situation is that you want to describe a space by algebraic equations. So in the simplest case, you just have a system of polynomial equations, and then you say, okay, the set of solutions of this polynomial equations, this will be called an affine scheme. This I consider as a space, and then I allow myself to glue more complex spaces from these basic affine schemes, and I call these more complex spaces schemes. Okay, so that's algebraic geometry. And what we do is we take HoTT and add a few axioms that I will show you on the next slides. And then we work internally to this, but to say that these axioms are justified, that they are consistent, we give a model, and the model is not infinity cuboids, which would model HoTT, but not the specific axioms for synthetic algebraic geometry. Instead, we take a different infinity topos, namely, roughly speaking, the Zariski topos. And a little bit more precisely, the model consists of cubical Zariski sheaves. And the good thing from an external perspective is that in this Zariski infinity topos here, you can find inside them the category of schemes. So schemes embed into the Zariski topos, meaning that from our internal synthetic perspective, we're talking about types all the time, and some of our types are schemes. So yeah, we will roughly see the definition of scheme in this. Right, so that is the situation. Now, let me start to show you these miraculous axioms that are supposed to be so nice, right? So here's the first axiom. We start with saying, okay, let's assume we have a commutative ring R, and this ring is local. So it makes sense to fix a ring because that's also what you do in algebraic geometry at the beginning of every talk. You fix a base ring. Usually you fix a field and maybe you suppose it's algebraically closed. So, but our base ring is just this R here. And what we assume for now is just that it's local. What does that mean? So remember, in the ring, you can add elements and you can multiply elements. Because you can multiply, you can ask whether elements are invertible. And then you can ask interesting questions about that. A local ring means that whenever you add up some elements and the result is invertible, then one of your sums was also invertible. That's a local ring, constructively. It's much weaker condition than having a field. Okay, so this is our base ring. Now, what do we do with it? We give the definition of affine schemes. The notation for it is this here, spectrum of A. So for this, we have to take finally presented R algebra A. So R is our base ring. We consider algebras over it. And yeah, we only consider finitely presented R algebras, but if you don't know precisely what it means, then not so important. And then we define that the spectrum of such an algebra is this set here, the set of R algebra homomorphisms from the R algebra A to the R algebra R. Why does this make sense? Because if the algebra A is presented by a list of polynomial equations, so if we have a presentation of A by a list of generators, which we think of as polynomial variables, and then a list of relations, which we think of as the equations in a system of polynomial equations, then you can check that this set of R algebra homomorphisms is in bijection to the set of solutions of this system of equations. So this says exactly, okay, spec A is the solutions of the polynomial equations that define A. So this makes wonderful sense. And in classical algebraic geometry, this is morally the correct definition, or what you should think an affine scheme you should think of as solutions of polynomial equations. But it is not technically good, because if we just take the set here in the classical algebraic geometry, it doesn't have enough structure at all. You have, instead of the set, you have to build a locally ringed topological space out of it to have enough structure that it behaves in the way you want. That is not what we do synthetically. We want to make our life easier, so we just consider the set and then impose an axiom that it behaves well. So that's this axiom here, which is called synthetic quasi-coherence, for reasons that I will not explain, SQC. It says that for each such A certain map is an equivalence, and the map goes from A to this function type here. So this is just alternative notation for function type, okay? The functions from spec A to R. Okay, so first of all, we can write down this quite simple map here that takes an element of A and turns it into a function from spec A to R. And the axiom says this is an equivalence. Let me do an example of what it means. My example is we take as A Rx, just the algebra of polynomials over X over R, right? I claim that the spectrum of Rx, first of all, is R itself. Let's check that. The spectrum of Rx is the set of R algebra homomorphisms from Rx to R. But by the universal property of Rx is freely generated as an R algebra from the element X. This just means pick an element of R. A homomorphism is the same as an element of R, and that's what this says here. So to be more precise, I should say spec of Rx is the underlying set of the ring R. And in algebraic geometry, you would call this the affine line. But anyway, we have this equation, and now we can plug it into the axiom. And what we get is Rx is in bijection to the function type from spec Rx, which is R to R. In other words, polynomials are functions, and functions are polynomials. So I think this is a very simple but somehow impressive application of this axiom, because it kind of means the world behaves algebraically. So however you define a function from R to R, it will always turn out that this function is a polynomial function. And also, two polynomials are equal if and only if they return the same result for every input. Okay, so yeah, this is an interesting axiom, and you can do a couple more quick applications to see more interesting things that I do not have time for now, but ask me later or ask some of the others. Yeah, I should just say, so these axioms hold in the model. So that's how nice the internal world of this system topos is. Okay, but now let's go on and try to think about how we should define scheme, because now we know what is an affine scheme, something of the form spec A. To define what a scheme is, we want to say that we can do affine schemes along open subsets. But what is an open subset? In algebraic geometry, the intuition is that if you have a function, then the set of points where the function takes invertible values is an open set. And that's exactly what we've defined here. The standard open set D of F is a subset of spec A, namely those points where the given function F is invertible. Technically, I have to apply X to F because X is homomorphism from A to R. But the axiom, the STC axiom of previous slide says that it would be equally correct to say f of X. That's how it is. So these are our standard open subsets. Now the thing is, this is even interesting if I apply it to the point. So if I apply it to the case A is R, you can check that the spectrum of R is just the point, the unit type. And this means that I have defined some subsets of the point. And I also want to allow unions, I want unions of open subsets always to be open, finite unions. So that's why I end up with this definition of when is a proposition open, when is a subset of the unit type open. The proposition is open if it can be written in this form. If you have elements of R such that the proposition holds if and only if one of these is irrational. Okay, so this is the general form of an open proposition. But now we have a slight problem or interesting situation because we know that we want these things to be open subsets of spec A, but we have an alternative definition of open subset of spec A, namely functions from spec A to open propositions, right? So these are the point-wise open subsets, and these are the things that we know we want to have as open subsets from the algebraic situation. So this embeds into this, but is it an equivalence? If not, then that's kind of a strange situation. So let's think about this for a very short moment. If I have a function from spec A to open propositions, I mean, okay, I know for every point the proposition whether this point belongs to my supposedly open subset. But what does it mean that this proposition is open at every point? It means that at every point there exist elements of R that give me the right open proposition. Okay, so I mean that this notation means a sigma type and a propositional truncation, yeah, because the proposition is open if there merely exists appropriate R1 to R1. Okay, so I have this function here, and at every point I merely know I have these numbers. What can I do with this? Nothing. I don't know how to go on. What would I like to have? At every point I merely have something. I would like to have an axiom of choice, because then I could pick at every point these numbers R1 to Rn. And then I could turn them into functions on spec A, right? The ith function picks out the Ri at every point. And then I could use these functions as elements of A, and then I could go on and prove that it comes from the left side. Does choice hold in the model? No. But something weaker, which we call Zariski local choice, holds in the Zariski topos. So I want to show you what this third and last axiom says. Here it is, Zariski local choice. It starts like one formulation of the axiom of choice whenever you have a surjection, but of a particular form that is a surjection into an affine scheme. Then the axiom of choice would say you can find a section. The axiom of Zariski local choice says you can find local sections. You can find a cover of spec A by these standard open subsets, and then find sections here. And the condition that these cover spec A is expressed in an algebraic way here by saying that the Fi are cofine elements of A. Okay, so yeah, I don't have the time to show the proof in detail, but this settles the question about open subsets. We can actually, using this, construct for every pointwise open subset, so to say, the algebraic witness that the subset should also be open in the algebraic sense. And now I just want to mention some more results that we can get from these three axioms. So the first is still about open subsets of spec A. Namely, they are in bijection to finitely generated radical ideals of A, which is exactly what you expect if you know algebraic geometry. And second, the open propositions are closed under sigma types. This is basically what you need to show, that an open subset of an open subset in something is also open in the big thing. So kind of subtle, but we can show it. And next thing, all functions from some affine scheme spec A to the natural numbers are bounded. So in a way, you cannot decompose an affine scheme into countably many disjoint parts. You always find a bound. And the type of schemes is also closed under sigma types, which is very nice because it means that when I have a scheme and I have a function to the type of all schemes, so for every point I have another scheme, then I can build a sigma type and get a scheme over my scheme. So a scheme over some x is the same thing as a map from x to, you could say, the universe of all schemes. This is very familiar if you talk about just about types, right? But here we have it for schemes. Okay, and then a bit more about cohomology, which I did not yet mention. So cohomology is defined in this way here. It is the same way. So this is, you could call it Eilenberg-MacLane cohomology because this K here denotes the Eilenberg-MacLane space. And we can define cohomology of an arbitrary type X actually with coefficients in a dependent A like this in this way here. It's the same definition of cohomology as in synthetic algebraic topology. But now here in synthetic algebraic geometry, it also works, and it is kind of astonishing because remember that spec A is a set, and also all our schemes will be sets, but still we can use the same definition here. Yeah, so they are sets, but they are definitely not discrete. You can get interesting cohomology. And then two things we know about this is that this definition of cohomology coincides with Czech cohomology, at least for separated schemes, and we can prove a little bit more. And so what is Czech cohomology? That is just the standard computational device that you use in classical algebraic geometry to compute cohomology of schemes. And so this is nice because this means we can compute it in similar ways for completely given schemes. And then the last thing, a scheme X is affine, so of the form spec A, if and only if all higher cohomology vanishes. So higher cohomology because n greater 0, for which coefficients, for coefficients given by a dependent R module on X, and we need a little technical definition here. WQC stands for weakly quasi-compact, and if you know from algebraic geometry that not all sheaves of modules are like good, but only the quasi-coherent sheaves modules, then this is what that corresponds to. Okay, that's all. Thank you.
Thank you. Well, we have a short time for questions. So, are there any questions?
Yes, okay. A scheme is viewed from affine schemes along open subsets. Said what affine scheme and open subsets are. So the technical definition would be a scheme is any type X, such that you can find finitely many open subtypes of X. Open here just means pointwise open, such that these open subtypes are affine schemes.
We give the microphone so this feedback also here.
Okay. I mean, you mentioned that these axioms have like a model, like there's a semantic. Can you say something more concrete about it? Like what?
Yeah, so I mentioned that the model is roughly speaking the Zariski infinity topos. There's the Zariski topos, and
so by infinity topos, I mean you take simplicial presheaves on the sides or something?
Yeah, no, we're technically we are using cubical. Where's it? Yeah, cubical Zariski sheaves. So, but I can't tell you all the details about that because I don't know all. But so the model is a combination of cubical sets model for univalence and the Zariski side, which is the side usually used for the Zariski topos. So it consists of trying to present the algebras over some data.
Yeah, so let's thank the speaker again. Go to the next speaker.